So last Friday, I was discussing the stable elliptic curve, and I was in some sense already introducing a new kind of analytic ring structure that we call the gaseous analytic ring structure. And so today I want to pick up there. And but to analyze this gaseous analytic ring structure, I will need to use some of the results that Dustin um, explained on Wednesday. Okay. But there's all about gaseous modules. And okay, so the plan roughly for today is to first say something about, I guess, what we call the gaseous spacer, which is a certain certain version of arithmetic long series. So this is in some sense some kind of subring of the wrong series in some variable that I was still called Q as last time. Um, then actually I want to take a little bit of time to talk about the corresponding theory over the real numbers, so about gaseous real spacers. And finally, I want to like the motivation for this was coming from the elliptic curve. And last time I saw a claim that this gaseous analytic ring structure would be good for that, and I want to start a little bit the explanation for that. So um, I want to say just a few words already now about the construction of the elliptic curve. Over this gaseous space, right? Um, but at that point, we'll have to do some more serious more analytic geometry, and I think that will be a point where we then will start to develop more of the general formalism to really carry that out. All right. So okay, so let's start with the gaseous space rings. So over here. Um, so recall that the motivation was to find the minimal analytic ring. A triangle mod A. Over which one can define the elliptic curve. And this is necessarily a bit imprecise because after all, the elliptic curve is an example of an elliptic curve, and the universal one would be then the moduli space of the elliptic curve. So this is not what we want to do. We really want something that is some of the form gm mod q to the z in some analytic sense. Elliptic curve E depending on some parameter Q. And so the errata were following that there should be this element Q, this should be a topological nilpotent unit. In the underlying condensed string. Yeah, call that one. And the second is the erratum that I mentioned, and I think is quite natural, but where I didn't so far didn't really explain, and maybe I will get to that towards the end of the day, why it's really the good condition is that if P is a free A module on a null sequence, let me call it, let me call it P tender. Right? So P is a free light condensed abelian group on a null sequence. Um, then 1 minus Q times the shift operator acting on P tensor is nice small. So this is similar to how we defined the solid analytic ring structure, where we had Q equal to 1 instead, and of course then we didn't ask that one is topology input. Um, I mean, this is some weaker condition because basically this is saying that for a null sequence, AN and A, we can form the sum of AN times Q. Right? So if you think about what the inverse of this operator would be, then it would be 1 plus Q times shift plus Q square times shift and so on. And so in particular, zero's coordinate would evaluate to such a sum. We can form some kind of geometric series in Q with the coefficients from a null sequence. And we certainly, I mean, we certainly want some condition here, right? Because if you didn't ask any kind of completeness condition, then we would just work with all condensed A modules. They wouldn't be completed in any sense, but we do want to be able to form some kind of infinite series. All right, and so something that I said last time was just clear, but maybe I should really say a few more words about this. Is that there is certainly an initial analytic ring with these properties. Uh, and you may or may not actually work with animated or infinity or whatever rings in the setup. The proof also shows that there's an initial animated such. Later on, I will actually compute the initial animated one and show that it's actually concentrated degree 0, and so then agrees with the initial analytic ring in the previous sense, which wasn't animated. Let me use a notation. So let me denote the free condensed rings on a topologically nilpotent element by Z adjoint Q hat. So this is defined to be Z adjoint Q to the n in infinity mod Q to the infinity is equal to 0. So actually, this is just P, right? Because I mean, it's just a condensed being group. I'm just taking Z adjoint any infinity mod infinity, which is precisely my definition of P. But then I'm endowing it with a string structure where I'm interpreting this n here is not the powers of some variable P. But I want to keep P sort of as a module separate from this kind of ring. So then we will certainly one corresponds to a math from this Z adjoint Q hat, and then we reverse convert to the X8 triangle. And let me call this thing here A triangle 0. So if we want 1, then we want a triangle to come with such a map, right? because there's a free condensed ring equipped with a topologically nilpotent unit. So there's a free guy with a topologically nilpotent element and this unit. Okay, so then we can form this free on the null sequence and send it up to this guy. And we have already here, we have 1 minus q times shift acting. And then we can define a certain full subcategory of all the modules over this ring. Like we want this to become an isomorphism. So in other words, whenever we map this to something over a module over an analytic ring, this should become an isomorphism. And so we can simply declare this to be all those modules over A0 triangle, such that 1 minus q times shift acting on the internal Hom from P. This is an isomorphism. And this is extremely analogous to how we defined solid modules, right? Where the ring there was just the integers, and then we asked a similar condition for q equal to 1. And because this internal Hom from P has such excellent properties, it's immediate to check, and this is more what I did for solid modules, that the subcategory has all these stability properties that we ask for an analytic ring. So then the fair A0 triangle, mod A, is somehow what we call, Dustin called last time, a pre-analytic ring, so some kind of non-complete analytic ring. So it doesn't satisfy, I mean, it satisfies all the properties of an analytic ring except for the property that the ring itself is complete. So the base ring is really just this uncompleted thing so far, and we need to do something about it.
But so shift is also.
But then properties 1 and 2, they precisely mean that our analytic ring could live over this pre-analytic ring. And so now we just use what Dustin proved on Wednesday, that the inclusion of analytic rings into pre-analytic rings has a left adjoint, so you can always complete such a pre-analytic ring. And so, yeah, as Dustin also explained last time, it's actually better to, when you have a general such analytic ring, to complete it in the sense of animated analytic rings. Because a priori the completion of the unit in this in the derived completion might not sit in degree 0, and then the better object to consider is the derived completion. In this case, it will turn out to be the case that this derived completion actually sits in degree 0, so there will not be a difference. So that's one reason that we somehow switched in this discussion about completion of analytic ring structures. The reason for the final stretch of Justin's talk last time was that we now want to compute this analytic ring structure. And for this, Dustin gave some general recipe for computing these completion functors in some cases. So we want to compute. Um, um, okay, so let me first give the formula for what this completion actually looks like. I already stated it very briefly last time, but let me elaborate. Okay, so the following. Grab the initial analytic animated. Um, Ring is above. But it turns out to live in degree 6. Let me give formulas. Yeah, so first of all, a triangle, but also all the free modules all the free A modules on light profinite sets, they sit in degree 0. So they have no homology outside degree 0. And they are also quasi-separated. So there's no house stop. So we're not describing some crazy things. Secondly, this A triangle, it is actually a subrange of the norm series ring. um, Let me first give the formula for the underlying ring. We will even a point. So these are those sums an times q to the n, such that the absolute value of an, I mean, certainly they're 0 for very negative n, very long series. But then when n goes large, they should have at most polynomials. And so this is tying things back to the discussion of the tape-elliptic curve,
He's building an
which
analytic structure from
has the property that when you write down the corresponding y-squared
So
equation, these are power
A0
series of cubes have this property.
and then he's completing it to get this analytic ring.
but that a
So is that the question?
Oh, I'm sorry. I didn't know we were mic'd up. Yeah, I answered it, I think so.
I'm also happy to answer it for everyone if it's
Yeah. Well, the question was whether the whether you're discussing a specific analytic ring here or some sort of general situation.
I'm just here. I'm describing, of course, the initial one coming from this proposition, the initial animator. Okay, so right. So I'm taking the underlying ring here in two levels, right? If you have an analytic ring, that first of all has an underlying condensed ring, and this has an underlying ring. So this is this one. And now if I also want to describe the condensed structure, then here's a way to do that. Let me try to write big so that there are no questions about indices. I take a union over k's and n's. So basically, k is giving me the polynomial growth and like the polynomial of degree k, and it's giving me the order of the pole of my wrong series, broadly speaking. And so then I'm taking a product over all n, which are at least minus n, of those integers which lie in the interval from n plus n to the k to n plus n to the k. Right? Integer in these bounds times q to the n. So each of the, I mean, this is always a finite set. So this product here is a light profinite set, and then taking the union of those. This describes this as a light condensed string, or it's a light condensed set first of all, but then it's a light condensed subset of here, and it's stable under the ring structure here. Otherwise, what? I'm not sure why I started calling it T. Let me switch to my usual name as please. Okay. So this describes this thing, and then it also describes the three modules. So for and the light profinite set written as an inverse limit of finite sets Si. A join S has a similar form. How did I decide to write it? Right. So first of all, again, you can think of this as like one way to say it if it lives in like you also on the Laurent series Q, you can take the guy on S and you can solidify that. So there's something where I understand. Let me recall that this is just the inverse limit over C power series Q join Si. That's it. Ignore the inverse of Q. Or in other words, these are some kind of zero series Q valued measures on S. Measures on S. these coefficient constants. Down it. So it sits inside there. So in particular, I only need to describe it as a condensed set, because the group structure will be the one on the target. And so one way to think about this is that, well, if you have an element here, some kind of measure, which is a sum over all m and v of some measures mu m times q to the n. And then again, I put a growth condition on the mu m's. So first of all, I actually asked if the mu m's, they are actually just sums of Dirac measures. So for any fixed power of q, you cannot really take an infinite sum here. This really must just be a sum of Dirac measures. Sorry, the statement of this. But even more than that, you asked that some of these are not too large. In terms of norms of the mu n's have most polynomial growth. And I guess, I mean, this is probably rather describing the underlying, like not the condensed structure. So let me describe the condensed structure now. And it's very similar to the above. So it's again a union over k's and n's. Playing the same role as above. But now we also need to squeeze in this inverse limit over all I to get something for S. And now we just do the obvious things. We take m greater or equal to minus n of the measures on Z adjoint Si, which are of norm at most n plus m to the k. Times Q. Right, so here you're allowed to take some differences of at most m plus m to the k basis elements. So if you did this when Si was just in one element, you would be down to that thing there. So this is just some finite set. This was some like profinite set. If you take this inverse limit over I, it's still some like profinite set, and then take this.
Peter, I wonder if it might be a bit clearer to just like drop the n greater than 0, only take the term n equals 0, and then just invert q on the outside.
Yeah, but then I would have to do this funny thing where I would have to replace n plus m here by something like n plus 2 in order for the zeros coefficient to be allowed.
Oh yeah, to be allowed to grow. Yeah, okay. Yeah, all right.
And then it looks artificial again. So
yeah, or you could have a constant c in front, like polynomial growth.
Well,
yeah, well, anyway. Yeah.
I was debating the best way to write this, but
okay.
This is correct, and you can certainly find many other ways to write this in units. And I thought if I'm already taking a union, then converting Q at the end seems like an operation too many. I don't know. It's a matter of taste, I guess. All right. Is that okay? So I don't want to give the full argument here, but I do want to provide a sketch. I want to at least explain where the polynomial growth condition suddenly appears, because this maybe is the most surprising thing. Because when we define this gaseous analytic ring structure, we didn't think of any specific growth conditions at all, right? We were just asking if 1 minus p times shift is convertible, and then we wonder what we're getting. And this is certainly also what happened to us when we thought about this business. So we just, well, let's write down this condition. It seems natural, and let's see what we get. This was what came out. So the way to compute this is to use the formula from the end of one weighted space lecture. So there was a formula how you compute some kind of completion in cases where the completeness condition is given by asking that the internal Hom or internal derived Hom from some algebra object is 0. So note that um, this condition that this internal Hom is an isomorphism is equivalent to the following. So that let me call it B set. So this is T into the A triangle. Mod 1 minus Q times. But now I actually I do want to think about P as a ring suddenly. So I said that I didn't want to do that, and I want to keep my notation separate. But at this point, I do want to remember that P admits a ring structure. And so then this is actually, I mean, it's a free guy on the topologically nilpotent element. So let me denote that by Z adjoin X hat as before. And then A hat was also a free nilpotent variable. And then, okay, so I had to invert Q. And then 1 minus, I mean, the shift operator is a multiplication by X. It's mod out by 1 minus X. So this is actually a commutative ring. So okay, so it's equivalent to the following condition using this P. So the condition is that the R Hom over a New York triangle from P, right? Because this R Hom is literally just the cone of this Homs, and the Homs are in degree 0 because of these external properties of P. And also, this B has a property that says internal R Hom from B commutes with all pole limits. Because, I mean, it's follows from the same property for P. So this was one of the conditions under which Dustin explained the formula for completion. I mean, the derived completion. In the three analytic rings. A0 triangle mod A is given by taking a module M, which is in the derived category of A0 triangle, derived category of condensed A0 triangle modules, and taking this to the sequential colimit of the following diagram. So M maps to the internal R from yeah, maybe I should give it a name. I will denote the fiber to the co-cone of point. So you can take the arm from I into, and because this fiber this naturally maps to one, so dually on R homes that map from M to this. And then there was some discussion last time about how to form the next maps, but I think it doesn't really matter all that much. We can go to applying the arm twice, which is of course just the arm from the tensor product. All right, so that's some kind of formula. And as Dustin mentioned last time, I mean, there are some situations where it's quite a useful formula. For example, if you're in a situation where you're just algebraically inverting some element f, so this would be some ring A mod f, then there's literally the usual way of inverting f where there's literally just always the same module and the maps are multiplication by f, and so then in the column you get m1 over f. But you could also try to use this formula to compute solid completion. But this turns out to be extremely confusing if you think about it. And yeah, maybe one thing that will happen is it's really only the colimit that's well behaved, both in the solid case and in this case here. And in the colimit, I claimed that you get something nice in degree 0, quarter separator, and so on. But each of the individual terms will actually be spread far out and have some higher homology, which is probably not quarter separator, and so on. So the individual terms are a bit hard to control. Right. So anyways, so how do we actually go about computing this? So this I mean, it's built from 1 and B. 1 is not so hard, of course. And B was just built from P, basically, by this code. So to understand what's happening here, the key is to understand what one key is certainly to compute the internal home from P. Internal home now from P, if we don't do the exchange, from A0 triangle, A0 triangle, but also A0 triangle. That's some S. And so basically, I want to evaluate this formula on the M's, which are some free guys on S, and then see what we get. And so here's the lemma. Let me make a remark that you don't actually have to invert Q in any of this. We can proceed without inverting Q. And then you will have similar. Yeah, the completion will basically be the same, except you drop all the terms which have negative powers of Q. Um, uh, and because it will be slightly easier to to write down the formulas if I don't have to invert Q. It will just be an extra operation. I have to do it every step. So then, if I don't invert Q, then this is really just the free topologically nilpotent element, which is just P. So one thing we have to understand is somehow what is the internal home from P to P, where we think of this here as say Z adjoint X hat and this adjoint. And there's a formula for this. So these three condensed abelian groups on some profinet set, they're always given as this union over all ends of like things which are bounded by norm n. And so this will somehow pull through this internal home, and so this will also be a union over n bigger than 0. Where now I'm somehow taking the part of this algebra here, where some of norm at most n. So at most n terms are allowed to appear. But then when I do that, some Q was topologically nilpotent. So now I'm allowed to do a limit over all n, which is like the power of Q I'm dividing by. And so then that's fine. So you take V adjoint Q, not Q to the n. But then inside this, you take sums of at most n basis elements. So you take sums an times Q to the ai times Q to the I, where the sums of the absolute values of the ai is at most n. And then you take polynomials in X, which I'm not sure whether I should call it X or X dual, but never mind. Let me call it. But it's also just a formal variable. So this is the part of the polynomial algebra where each coefficient satisfies its bound. Okay, and so there's a similar formula for the internal home from Phi, which I again think of as Z adjoint X set, towards Z adjoint Phi hat adjoin some light profile at S. And it's just the same, so to speak. So you take a union over all n bigger than 0. And I take an inverse limit over all n. And then you take a V adjoint Q, not 3 to the n, adjoint Si. But inside there, again, this part that's sum of at most n, sum of difference of at most n basis elements. Maybe I should put some operators. And then I take a polynomials in the dual variable. Right, where each term satisfies this bound. All right, so you get
Peter, just a point of information about the way things look on the screen here. So if you're close to the boundary of the board, like the far right of the right-hand board or the far left of the left-hand board, it's quite a shadow, and we basically don't see anything.
Is that still okay, or is it also too far in the shadow?
That's better. That's readable with some effort. Yeah.
Give us any limit over the height. Yeah, sure. Yes, of course.
What is the stop in the exponent of the x?
Sorry, x, maybe I should give it a different, it's called y. It's just a different.
Okay.
I didn't want to call it x because it's some of the dual of x. Or, yeah, but because maybe I used the head to have some specific meaning here, the star didn't have any meaning in that sense. So in particular, one way to a consequence of this is that this internal home from P to P is actually just the subspace of uh, Z adjoint Y power to Q. And it's a subspace with a certain kind of funny condition that sorry this. So some kind of, let me denote this by P adjoint Y power series and Q bounded. Because in some sense you're asking that yeah, there's some boundedness in terms of the coefficients of uh, of all the y's. And similarly, the from P to this P going to have join S is also a subring of you take Z adjoint Y, and then you take join S, and then you take power series in Q. And again, it's a subspace of this where each coefficient of Y satisfies a certain boundedness property. So again, I will denote this here by P adjoint Y adjoint S power series in Q bounded.
Peter, there's been a request to explain again what the less than or equal to n means in the description of Hom from P to P.
For a finite set I, I didn't use I for anything here, right? V adjoint I less or equal to n is a certain subspace of V adjoint with a free finite free being groups on I, and a set of those sum over I of some AI times I. So that the sum of the absolute values of the AIs is at most n. All right, so if you take this formula for the internal home from P and just do these formal manipulations that you express I in terms of the other thing. Sorry, this board is way too high. If you just do these formal manipulations, then you, for example, see that the R home I said I didn't invert Q, so let me explicitly say just for Z join Q hat. And okay, so I can also be defined of corresponding version without inverting Q hat. So if you compute that, then this is a two-term complex. Where those terms are being computed up there. If you take this these power series over here join Y, which have some bounded coefficients. And previously there was some transition map that was 1 minus x times q. But now y is some kind of dual of x, so now actually in the transition map turns out to be just q minus or y minus q minus 1. And so this sits in degree 0, and this sits in homological degree 1. And if you do the similar computation with more variables, if you take k tensor factors here, then you get a similar picture, but just k of the variables y. So this is computed by a possible complex in y of this variable. So instead, what you somehow take is you take z and then you join y1 up to yk. And then again, you take such bounded power series in Q. And then, I mean, some of this was the derived quotient by just one variable q minus y. And now you take a derived quotient by q minus y1 up to q. So the derived quotient corresponds to taking a fossil. And I mean, you can do the same with a set S in, right? So if you have a profile set S somewhere, then you just plot the profile set S here in the middle and then get the same form. So similar form. All right, and so now we have a somewhat concrete formula for these things, right? So if you want to compute the underlying ring, we literally just have to understand the colimit over all k of these things. So thus, the ring we're interested in is just the co-limit over all k of this thing. Take y1 to yk, power series q bounded, and then you take the derived quotient. And here it turns out to be a case where it's really a priori important at each individual level to take the derived quotient. To the full causal complex, because there will be high homology. Right. Then here, plug in this S.
What are the transition maps?
The transition map, sorry, yeah, I should have said. So this is a similar question to what the transition map is calling that Dustin wrote down last time. You just, I mean, each of these is a suffering of the next one where you just don't have the new variable.
Okay.
All right, it's not a story. All of these things are actually not rings because if you multiply two things, no, sorry, what? Confusion, but let me not try to say whether they are rings or not, but I mean, certainly there are submodules for you. All right. So far there was no apparent polynomial Rose condition at all. There was just some kind of boundedness that appeared for more transparent reasons. But now let's analyze like the exterior of this, or rather a separated quotient. So I mean, this is for simplicity. Yeah, you can do a full analysis, but it takes a lot of concentration. So I think there's already enough interesting stuff going on without these additional technicalities. So right. So what is the H0? So you really just take this ring and then mod out like q minus y1 up to q minus yk. Or if you take the separated quotient, really by the closure of all these things. Yeah? So in other words, you're somehow formally allowed to replace any occurrence of any of these variables yi that is really just setting for q. Right? So this basically the question becomes, what is the image of this thing mapping towards power solution Q, where all the yi goes to Q. So let me again recall what this was. So this was the union over all n of of the limit over m of the part of this a thing which was of norm at most n. So this wasn't literally written as a finite free module, but I mean, it takes the basis by giving my 1q up to q to the n-1. And then you count the variables by one squared. But in particular, it will actually be sufficient to analyze the part where all of these are, say, just equal to 1. 0 or 1 or something like this, or -1. So here we're just allowed to take some kind of bounded sum. But then we have all these y1s through yk's here at disposal. But for each of them individually, I mean, just each coefficient individually is bounded. So for example, if like for each n, we have to analyze what the image is. But then which multiples of q, which like integer times q can I achieve? Well, this integer times q, like for each occurrence of q, I can decide whether I want to keep it a q or whether I make it a y1 through yk. But for each y1 through yk, I can somehow use at most n times. But then in total, like there are kn, I can get this variable q k n k times n times because yeah, there. Um, and then actually maybe the n is rather a red herring, so let's ignore the n. So if n was equal to 1, then we couldn't somehow get a coefficient up to k here for this q because I can somehow split each occurrence of q between the different variables. And then if I look at q squared, then I have all the monomials of degree 2 here at disposal in the y1 so yk. So there are like k over 2 monomials I have at disposal. Each one I can use like at most n times. So I get n times k over 2. And then in degree some big M, sorry, it's k plus 1 over 2, I guess. I have k plus m over m choices for these monomials here. So the coefficient of q to the n can lie in like minus n times n plus k over k up to the same thing. And maybe I didn't like maybe I would have to be slightly more careful here with precise noise, but I mean basically something like that. And so the question is somehow how does this grow in n? And in n, this is precisely a polynomial of degree k, right? And n is just a polynomial function of degree k. Yeah, so whenever I have something that grows in, but the coefficients grow in n just like polynomially, then because yeah, I have all these monomials here at disposal, I can somehow split up all the individual summands to make them bounded in here. And there's a lot of choices about how you go about doing this. And when you want to prove that actually this Kosovo complex ends up being in degree 0, you somehow have to show that a different way of arranging the terms here is actually like differs from the other one by something bounded, some bounded sum in the next term of the complex. And this will actually not be true for a given k, but when you allow you to increase your k a little bit, then you can do it.
Peter, there's a question in the chat.
There's a question in the chat.
Yeah, which is or you want to read it or?
Yeah, so there was a question about this Z adjoin Y adjoin S whether I can interchange the order, and indeed you can interchange the order. And so the kind of argument you have to do here to see that this well behaves is a little reminiscent of the arguments you have to prove that the liquid analytic ring structure is well behaved, but it's several orders of magnitude easier, right? So it's again a situation where you have some kind of system of complexes where each term has some kind of norms, and then you have to like see that if you have something with differential zero, you can find some kind of bounded preimage. But here it's really, you can really just do it. I mean, it takes some concentration, but it's not all that difficult. All right. All right. So this is all I wanted to say about the proof of this. So the box and quotation marks here. Now I want to talk just briefly about gaseous real vector spaces. So let me give the definition. Condensed or light. And we started emitting the light at a couple of times. So throughout this course, we're always working the light filling, and it might not always be mentioned. Yes, it's if when you take the internal home from like P was always knowing the free-ground null sequence with integers. So just here. And then I choose one topological equipotent unit in the real, say a half. So now you might actually wonder, does it matter that it shows a half here? And it doesn't. So I mean, so in this series of liquid analytic of these liquid ring structures on the reals, there was this extra parameter that you have to choose your how non-convex you allow your vector spaces to be. Here it seems you also have to make a choice, but actually it doesn't matter. The condition is independent. For the choice of number like a half, that lies in the open interval. Or you could also take it negative, I guess. Any topological unit would do. Actually, why? So it's easy to see and intuitively believable that if you make this number smaller, then the conditioning becomes weaker because you have some of the series you're trying to sum there, like even faster decaying. But on the other hand, if you're trying to sum a geometric series where the coefficients are like 1/2 to the n, then you can always write it as a finite sum where you sum the first few terms and then some kind of telescoped, or not really telescope, but yeah, let me write it down.
There's another question in the chat. I actually missed it, so I can't read it.
Let me see if I can read it. By the way, general question. Non-light condensed sets will not be used anymore in the series. Originally, right. So there was a question, like originally extremely disconnected set played quite a crucial role in how we set up the series because it gave us enough projective objects and it is really quite convenient to have. So for much of what we're doing, we're kind of forgetting about the full category of condensed sets. But on the other hand, for some arguments, it actually is still quite convenient to have the ambient framework of all condensed sets. Because I mean, the light ones, they still embed into all condensed sets. And for some so if you want to check that something is an isomorphism, you can still do that by checking the values on extremely disconnected. And this is still convenient for a few arguments. So yeah. Yeah, I mean, the other setting is also nice, but like for the specific application analytic geometry, we found it more convenient to make this restriction because there are a couple of things, in particular, this internal projectivity of P that we're using all over the place. That's only from this thing. Maybe related questions like, can you also, like the theory of liquid real vector space that also worked not just in the light setting, but in the full setting, you can ask the same question about the gaseous analytic ring structure, whether you can also define that on all condensed R modules. I think you can, but the argument we gave here does not work because we use internal projectivity of P. So you would have to argue slightly more carefully to see that there is a good analytic ring structure of gaseous real vector spaces in the full condensed setting. So generally, 1 minus Q times shift is not isomorphism if it only it's 1 minus Q to the n times shift. Isomorphism. Yeah, and this is basically a telescopic argument. All right. I mean, if you want to sum a n times 2 to the n and n times 2 to the n. You can always rewrite like this and as a finite sum, and then a new sum where you still have a null sequence of coefficients and now powers of 2 to the n here. All right, so you have let's say. And so anything that's P liquid for any P or alpha liquid for any alpha is always gaseous. So this is an extremely general class of condensed real vector spaces, but it's still a workable class for many purposes. And so you can now wonder what are the three gaseous real vector spaces. And here's so first of all, yeah. So here's the proposition. What does it have to do with what we had previously? So our gas, which denotes the analytic ring corresponding to gaseous real vector spaces. So again, it's clear that this defines an analytic ring structure because of these good properties of P. This is just gotten by taking this one we had. Here's a ring version. Like the completed one. And the gaseous modules over this. And then sometimes modding out by 1 minus 2 times Q. Setting Q equal to a half. If you take this one, you complete that analytic ring as we did, and then you set Q equal to a half. So it's easy to see that when you do this to this ring, this is polynomial growth condition that you're getting, you actually get the real numbers. That's okay.
You don't take some all.
Hmm?
You don't take some all in there.
You don't?
And some all. What's the thing?
Yeah, no, I mean, like, if you take this completed ring and model by 1 minus PQ, you really get the real number. I mean, so these are like functions on like the real part of this thing is like a function of open unit just over the real numbers. And then if you set Q equal to a half there, like this one-dimensional thing, you just get the real numbers. In particular, this tells you what the free Gaussian language are. You can compute them the free Gaussian real vector spaces by taking the free guys here and then taking this quotient. But now the description becomes a bit confusing because when we wrote down the growth conditions that we allow here, it was some kind of polynomial growth condition in Q. But now Q has become a constant, so it's not immediately clear how you rephrase these growth conditions directly on the real numbers. But you can do it. And here's the description. So the free gaseous real vector space on some light profinite set S has the following crazy description. They take a union over, again, some case, which corresponding to this polynomial growth that we had previously, and now there is a constant. Then I take a limit over I. And then I take a certain bounded subset in the free real vector space on the finite sets Si, which satisfy some condition on how large the Xi's are allowed to be. And the condition is that if you sum the Xi's and measure it, or their size measured in terms of certain functions fk that I will introduce in a second, there it goes to C. So formally, this is very similar to what the free liquid vector spaces look like. And there, the norms you were taking there were like, you were raising to some power alpha, or maybe beta, or beta plus and alpha. Generally, the functions that you would like to put there, they should be increasing, of course, because larger x's should be penalized more. On the other hand, you want the transition maps to be well-defined. And for this, you need the functions to be concave, turns out. So for this to be reasonable, these functions fk, they should measure how large the real number is in terms of some letting it to some real number greater or equal to 0. I mean, they should be increasing and concave. So basically, you need that fk of x plus y should be at most fk of x, but fk of y. If you want the transition maps there to be well-defined, because the transition maps are somehow summing some of these x's. And this is ensured by the concavity. But on the other hand, you don't really care what your function is for large values of x, because Really, what you're trying to single out is just which infinite sums are allowed. And of course, in these infinite sums, almost all the terms should be very, very small. So when I choose such a function fk, really only the only thing that matters is the behavior near zero. Okay, so this is a prelude to saying that so fk is any increasing concave function such that for small x, it's given by the following. It's the absolute value of log x to the minus k. So I'm saying it this way because, I mean, in principle, I'd just like to take this function. And in the neighborhood of zero, that is a nice increasing concave function, but then at some point, it becomes convex, goes to infinity, and then does some nonsense because, like, if you say x equal to 1, log of 1 is 0, 1 to the minus k is some nonsense. So, so I can write down this function for all x, but I can do it for small x, and then at some point, I just arbitrarily extend it. It doesn't really matter. All right, so this is maybe a little bit hard to digest. So let me give a sort of diagram. So in the liquid case, in the liquid story, uh, there this function f of x somehow the absolute value of x to the beta, where beta is some number between 0 and 1. So there's some function. So this is always increasing in concave, so I can just always use it. So it's some function like that. And then the locus where the sum of the x to the beta, to the beta x to the beta, so close to c, in the two variable cases will be some kind of locus like that, some slightly non-convex thing. In the gaseous case, it's some function that's extremely steeply ascending near 0. So even if it's just a tiny number, it's often treated as rather large by this function fk. Then the actual function absolute value that I wrote there would make a turn and then go up, and okay, instead I just cut. I can make it linear if I want to, right? Need not be strictly convex. And then if I look at the set where the k of x is, this will similarly be something that's extremely closely tied to the coordinate axis. So you're allowed to take certain infinite sums, but basically you have to ensure that the coefficients have exponentially k. But not quite that actually. So from the liquid theory, we can form some of some xn. When there exists some beta less than some pre-specified alpha, such that the sum of the xn to the beta are finite, so they're beta summable. I in principle would like to just ask usual summability, but as I said, this doesn't really work. But when you slightly restrict the class of sums for which you're asked that they are always like part of the structure of liquid real vector space to be the beta summable ones, then this works. In the gaseous theory, you have much more stringent conditions.
What's alpha?
So yeah, it's in the alpha liquid theory. So the liquid theory is dependent on the extra parameter. The gaseous theory can only form those sums where there exists the K, but the sum of the K are nice. And this actually drew on to saying that the xn up to reordering. So if you sum them in the order starting with the largest ones and descending, then the xn have or the 1 over xn has the xn inverse, sorry, the xn inverse should have probably exponential growth. By which I mean the following. So you can form such a sum if and only if there exists some epsilon greater than or equals to 0, and maybe some constant c greater than 0, such that the absolute value of xn is at most c times a half to the n to the epsilon. Right, so if I didn't put the epsilon here, then this would be some kind of exponential decay. It's enough to have some fractional power of n here in the exponent. And if they satisfy some decay condition like this, then you're allowed to sum them with guesses. So why does this expression appear here? Well, if you take a half to the n to the epsilon and then apply this kind of procedure here, then the log turns this into n to the epsilon. And then to the minus k, you get 1 over n to the epsilon times k. And this becomes summable when, I don't know, epsilon times k becomes greater than 1. All right, so it's some rather crazy type of growth conditions. One gets here with real numbers. But it's still a workable thing because, like, Dustin and I gave this course on complex geometry. And at least all the stuff in complex geometry would work as well with gaseous vector spaces, because the only thing that we really needed were that these algebras of overconvergent polymorphic functions were some kind of nice thing in the theory and with some nuclear. And this is still true in this story. Because the transition maps, when you form, like when you restrict holomorphic functions on one disk, holomorphic functions on a smaller disk, then you're precisely, if you think in terms of their power series expansions, you're precisely rescaling all the power series coefficients by fixed power of a number less than 1. So actually the transition maps, they have exponential decay. So yeah, so I think the gaseous story would be just as good for this discussion of complex geometry. All right. Um, yeah. So so the claim is that you can do this computation of the three gaseous real vector spaces formally from the one I did over this gaseous space string in the variable Q. Takes a little bit of unraveling, but it's not all that hard. All right, so finally, let me try to do some geometry. Geometry. So the goal is to define elliptic curves. Q over this gaseous space string. Okay, let me again record it. H1. And so the idea is something that we already used a couple of times. Uh, we have this fixed topic in the nilpotent unit. Q. And like an Analytic string, we somehow use that whenever you have fixed topology nilpotent unit, you can use this to normalize absolute values. So that somehow when you want to understand how large some other function is, you can see some how large it is compared to Q. So we can use Q to measure the size of any other function. So basically, you're wondering like, how do powers of the absolute value of f compared to powers of the absolute value of q? Right. Um, and one way to organize this information is in the following place. And now I will start to use this formalism of analytic stacks that this whole course like, is the main aim of introducing. And this language is really convenient to phrase the following plane because I could give a more down-to-earth version of this, but it would be much more confusing. And or I don't know. I think it's a really neat way of packaging the information. I will maybe explain a little bit about this information. So there exists a morphism of analytic stacks to be introduced. From let's say first from the you have the affine line over A. And on the affine line, you have the coordinate function. In particular, like when you want to do something for any function, you can sometimes do it for the universal function, which is the function t on an A1, right? So whenever you have any function on A, then this gives you a map from the analytic spectrum of A to this A1, mapping your function t to your. If you want to define something for any function, it's somehow enough to do it for an A1 in the universal case. And so then there is some kind of absolute value of t function measured against the absolute value of q that goes to, well, in this case, it can actually be infinite. Because it could be some kind of unbounded function. Maybe a better way to think about this is that you have one on the projective line. And so if you have the point, this homogeneous coordinates t1 through t2, then this one goes to the absolute value of t1 over t2. Implicit here is that something is down to earth as this closed interval will have a certain very crazy incarnation and an analytic stack in our setup. And this is required to make sense of this maths. So implicit here again is again, so if you really want to go to zero infinity here, I again need to normalize the absolute value of q, and so I do what I always do, I set it equal to r. But I mean, in my last lecture, it kind of suddenly mattered at one point what I showed there, but here it doesn't matter again. And always just rescale. But let's assume we're in a formalism where something like this makes sense, where we have some kind of way of measuring the absolute value on this thing. Something there. So then we can define what I call the analytic chain over A as a preimage of the open part theorem to infinity. So this is intuitively speaking the union over all n of the locus where the absolute value of t is bounded between some powers some powers of the absolute value of q. Right? And this was something that already entered at the beginning of my last lecture. That this is somehow what you should start with if you want to define the tailor-elliptic curve, and then define that. And then you still have acting on this multiplication by q. And this map here is actually some kind of multiplicative map. So if you multiply the absolute value of the product of the absolute values, where this, if it so happens that one is 0 and the other is infinity, then there's no claim being made. But in particular, on this locus, I mean, you have this analytic gem mapping to 0 infinity. You have multiplication by q here. This corresponds to by multiplication by a half here. And this map here is actually some kind of proper map because P1 is proper, 0 infinity is proper, so the map is proper. So you have a proper map to here. And then if you pass the quotient, then you have GM walking by Q to the Z. Right, I mean, this must be totally discontinuous. I mean, free and totally discontinuous is actually because it is free here, right? So this then is just fibered over 0 infinity modulo half 2Z, which copy of the circle. So the map is it's locally isomorphic to this map, so this map is proper. But now S1 is again some nice proper thing. And so this means that this one is proper. But of course, it's also locally isomorphic to this one, which is an open subset of P1, and P1 ought to be smooth. So it's a proper and a curve, so this must be a proper smooth curve. And this is the table. Right? And so this is how we want to argue how we can construct the take elliptic curve. All right, shall we start? Questions?
This 0 infinity is also defined over this A.
You can base change it to A, or you don't have to, right? I mean,
Okay.
yeah. And this is over A, so you can always have to base change. You can or cannot do it.
It's different from usual 0 infinity.
What is the usual 0 infinity?
Suppose just say 0 infinity.
No, I mean, there will be a functor from light condensed sets towards analytic sets. And so 0 infinity I consider as a light condensed set, and this will have an incarnation as an analytic star. This will actually mean that the theory of analytic states will be related to the condensed story in two ways. One, because like the analytic rings themselves are founded somehow on condensed things, which is the role that condensed stuff played so far. But suddenly there will be another role that the condensed stuff plays because, yeah, the condensed sets, they will also have an incarnation in the world of analytic statics. And then actually two kind of somewhat orthogonal condensed directions in the picture. Because the way this thing will be realized as an analytic stack, it will actually just use discrete rings. It will not use any interesting condensed structure on the ring level. Anyways.
Thanks, Peter.
Yeah.